All right, let's just jump right into it. Welcome to The Explainer. Today we're unraveling the true, completely mind-bending timelines of solar system exploration. We are going to map out exactly how long it takes to reach other worlds and, honestly, more importantly, why those journeys take as long as they do. Okay, let's dive into this. So, how long does it actually take to reach Mars? You know, it's a question that naturally tricks us. We do this quick mental math based on history, right? The Apollo missions reached the moon in just 3 days, so intuitively we just assume that if we point a rocket at Mars, our next-door neighbor, it might take a week, maybe 2 weeks if we take it really slow. But that intuition is completely 100% wrong.
And the reason why is pretty fascinating. You just can't point and shoot a rocket directly at a planet. It'd be nice, but no. The solar system isn't just a set of fixed targets. It's this giant, incredibly complex moving machine. Planets travel in stretched ovals called ellipses, which means the distances between them are constantly changing. If you aim directly at Mars, well, by the time you actually cross that distance, the planet has already moved on without you. On top of that, your launch window dictates your starting distance, and that can vary by literally hundreds of millions of kilometers.
So to actually navigate this machine, you have to use what's called a Raman transfer. It's basically a flight path shaped like half of an ellipse. Think about throwing a deep pass in football. A good quarterback doesn't aim right at where the receiver is currently standing, they aim at where the receiver is going to be. The Raman transfer does exactly this. It is incredibly fuel efficient, but it comes with a massive, massive cost: time. Now, to make these truly massive journeys even possible, spacecraft rely on another little trick: the gravity assist. Basically, by swinging really close to a planet, a spacecraft can literally steal a tiny fraction of that planet's orbital energy. It slingshots out the other side way faster than it arrived, all without burning a single drop of extra propellant. It's honestly the closest thing to a free lunch in physics. Voyager 2 actually had to chain 4 of these gravity assists together just to reach Neptune, simply because a direct flight would require impossibly huge rockets that we don't even have.
All right, moving on to part 1. Navigating the inner planets.
You might not guess this, but reaching Mercury is ridiculously difficult. And not because it's super far away, but because it sits deep inside the Sun's massive gravity well. As a spacecraft heads inward, the Sun pulls it, accelerating it wildly. If you just want to fly by, kind of like Mariner 10 did back in 1973, it takes about 6 months. But to actually stop and orbit Mercury, you have to shed an enormous amount of speed. The Messenger probe took 6.5 years, threading multiple gravity assists just to hit the brakes hard enough to stay in orbit.
Moving out just a bit to Venus, we're looking at a world that is basically Earth's evil twin. I mean, the atmosphere there pushes down with 92 times Earth's surface pressure, completely trapping a runaway greenhouse effect that bakes the surface at 465 degrees Celsius. Needless to say, not a great vacation spot. And that horrifying chemical pressure cooker is exactly why the incredibly durable Soviet Venera landers, which are still the only spacecraft to ever transmit images from the surface, survived a maximum of just 127 minutes before being totally crushed and melted.
So, bringing it back to Mars for human missions, the transit realities are honestly pretty daunting. Using standard chemical propulsion, that agonizingly slow Raman transfer takes 7 to 9 months, one way. Plus, you're dealing with a 12.5-minute light communication delay. But the real issue here is biological. Astronauts face severe, still unresolved challenges, massive bone density loss from microgravity, and a cosmic radiation dose of around 0.66 sieverts, which drastically increases lifetime cancer risks. Our current chemical rockets are pushing their absolute limits with this.
Okay, that brings us to part 2, the giant hurdle, or crossing the divide into the outer solar system.
Let's take Europa, for instance. This moon is arguably our absolute best bet for finding alien life right now. It has a subsurface ocean with more liquid water than all of Earth's oceans combined. But the environment is violently hostile. Jupiter's magnetic field creates a radiation belt so intense it would deliver a lethal dose to an unshielded human in just 10 minutes. That's exactly why missions like the Europa Clipper can't just orbit it directly. They have to fly past it repeatedly from a much safer Jupiter orbit to avoid having their instruments completely fried in a matter of weeks. And you know what's really interesting here is the wild contrast in travel times depending on what you want to do. Pioneer 10, it flew past Jupiter in just 640 days, but Galileo took 6 whole years to arrive. Why the huge difference? Well, if Galileo had arrived at Pioneer's speed, it would have shot straight past Jupiter and deep into space. Galileo had to literally loop past Venus and Earth, carefully bleeding off speed so it could arrive at Jupiter slow enough to actually get captured by its gravity and enter orbit.
The absolutely epic timeline of the Cassini mission to Saturn is pretty much the ultimate example of this kind of patience.
Cassini launched way back in 1997, and it spent 7 long years just threading gravity assist to arrive at the exact speed required to safely orbit Saturn. But that 7-year investment bought us a 13-year study of Saturn's rings, the methane lakes on Titan, and the incredible water plumes of Enceladus, all before it was deliberately crashed into Saturn in 2017 just to protect those pristine moons.
So, let's push even further out. Part 3, reaching the outer edge. Uranus is, well, it's truly bizarre. It tilts at an extreme 98 degrees, meaning it literally rolls on its side as it orbits the Sun. Plus, its magnetic field is wildly offset, and it radiates almost no internal heat whatsoever. We've only ever visited Uranus and Neptune once, and that was back in the 1980s. Voyager 2 only made it there because engineers took advantage of this incredibly rare 76-year planetary alignment to slingshot the probe outward. Talk about perfect timing.
And then there's the 9.5-year sprint to Pluto. To reach the former 9th planet, the New Horizons probe had to absolutely blast across the solar system, traveling at a mind-bending 57,600 kilometers per hour. When it arrived, it discovered these incredible active nitrogen glaciers. But remember, it was just a flyby. Orbiting Pluto at that speed was completely impossible. To carry enough propellant to actually hit the brakes, they would have needed a rocket 4 times the mass of the launch vehicle.
So what does this all mean? Well, it really all comes down to what we call the stopping problem. You see, the real limiting factor in spaceflight isn't actually going fast. It's hauling enough heavy fuel across millions of kilometers just to hit the brakes. Braking in space costs exactly as much energy as accelerating. And because fuel is heavy, carrying enough fuel to stop means you need a bigger rocket to launch that fuel, which requires even more fuel. It's just this vicious exponential curve.
So how do we fix this? Simple. We desperately need better engines. Standard chemical propulsion strictly limits us to that 7 to 9 month trip to Mars. But nuclear thermal propulsion, that's a real game changer. It uses a fission reactor to heat hydrogen, and it is vastly more efficient. While it's still in the prototype phase, this tech could theoretically cut human transit times to Mars down to just 3 to 4 months. Honestly, if we ever want to truly become a multiplanetary species, this is arguably the single most important investment we can make. But, let's take a step back for a second. Carl Sagan once famously said, "Somewhere, something incredible is waiting to be known." And that hits the nail on the head, doesn't it? Whether a mission takes 6 months to reach Venus or 13 painstaking years to map Saturn, every incredibly slow, agonizingly difficult trip we've ever taken has fundamentally changed our entire understanding of the universe. The payoff has always been worth the wait.
Which leaves us with one final big question. Where are we going next? The solar system is a vast neighborhood, and frankly, we have barely even started exploring it. So the next time you look up at a steady point of light in the night sky, realize you aren't just looking at a planet, you are looking at a destination, one that takes years, sometimes decades, to reach with the absolute greatest machinery humanity can build. But as history shows us, the trip is always worth making. Thanks for joining me on this explainer, and keep looking up.